Good evening, and welcome back to Vegas October 1 Sounds. Tonight, I'm going to have just a short conversation, and it's a paper that I ran across recently, and I'd like to review it with you because it kind of has better pictures than I've had in explaining some of these things. So before we get into this paper, and this is a terribly simple paper, and it's a paper that has been submitted to and or part of NATO by a research group to help try to set the standards and metrics by which shooter localization systems should perform. And this company is making a proposal to NATO based upon the product that they've done, and they're hoping that for that type of product, and not all products fit into that category range, that NATO will adopt these standards. Now, this document is fairly old. It's October of 2006, and well, what can I say? It's almost 14 years since that time. But the overall research that I've been doing isn't, fairly complex in terms of the sophistication of the algorithms that have been developed since this time. In fact, all the research that I'm doing is very similar to what was going on about 12 years ago. So, these guys talk about, like things like, if we have a shooter localization system, and it's going to determine a few things about the rounds or the shots being fired, how accurate should the system be if it's going to be effective in the field? And they define, the types of field environments they have, the types of the system that they're using, and how it should perform to try to help NATO or to persuade NATO into adopting these. All right. For long-term listeners to my channel, there's probably not going to be a lot of new information, except that the pictures these folks use are perhaps a little bit more explanatory than what I've been doing, and in particular they cover two different cases. But before we get started, let's go ahead and read part of this stuff. And you can go read this paper. All you have to do is search for performance metrics for acoustic small arms localization systems in your favorite search engine, and I'm sure it'll come up as a PDF. All right. So, acoustic phenomenology. What a long word, huh? Basically, they're saying that, what are the acoustic phenomena is associated with small arms fire. And they go on to explain how there's predominantly two sounds, the muzzle blast and shock wave. And then they refer down to this figure. And they tell you that the muzzle blast is created by the rapid discharge of the propellant and the fast combustion of that unburnt part. And that the shock wave is created by a supersonic bullet traveling through the air, and similar to a supersonic aircraft. Old stuff here. Then they go on to explain that from the perspective of their sensors, and their sensors is a microphone array that they have built. The muzzle blast, which they show over here as these little dotted lines, can be considered a point source. Yes, it sounds familiar, doesn't it? And that it propagates spherically from the muzzle at the speed of sound. And again, that sounds familiar. And they have this nice little diagram for it. And then they go on to say that it can be detected from anywhere, around the firing position, provided that there's no, obstructions in the path, and that from the perspective of this microphone, it's a direct path to the weapon. So, in this case, what we have is, and let's make this picture a little bigger, and we may have to do some drawings. This is case one. This is the case where the observer, in this case the microphone array, is fairly close to the line of fire of the bullet. In which case that the muzzle blast, and you can see by these little arrows here blue for the muzzle blast wave, and red for the shock wave. The approximate, or relative ratios of when those sounds are going to reach the microphone. For the shock wave, it's going to be, quick, and for the muzzle blast wave, it's going to be fairly long. And they talk about the angle of fire, which is the angle from a clockwise direction from the line of fire to either the muzzle wave or anything else you want to measure. They also talk about the supersonic cone here, which is the red lines. And again, this is a 2D projection of a 3D phenomena. Alright, and they show that the propagation direction of the supersonic shock wave here is parallel to the cone, as you can see by the little red dotted lines. So this all kind of, is review material, but what it does is it puts in perspective in a little bit more colorful way what I've been saying. Now this is the case where the microphone or the observer is downrange from the shooter, and that range is larger than the miss distance or the propagation path of the shock wave from when it was created by the bullet. Before I get into a lot of detail, they present another variant of the ratio of muzzle blast to shock wave in the next image, in the case where the observer is at a great angle here, is a large angle between the line of fire and the muzzle blast, i.e. a large angle of fire. In that case, the two propagation paths for the shock wave and the muzzle blast wave are getting much more similar, and you can see by where the little red and blue arrows are that the arrival times are going to be somewhat close together. And so these are the two cases. Now in reality, you can have both these cases produced by the same bullet if you have two different observers, and that's been the whole point of much of my emphasis for the past few weeks, is this discussion of how the arrival time of the shock wave is really a function of several different things. You can measure it as downrange distance along the line of fire plus the cross range, or you can measure it line of fire or by the angle of fire. But once that angle of fire gets large, or similarly the cross range distance is large, then these paths become very similar. So before we get any further, let me draw a picture of when they happen at the same time. So if we've got our gun, it's located over here, and I'm going to draw the gun fairly up high, and I'm not going to draw any angles tonight for elevated position. If we fire a bullet and it goes out here, and let's presume it's a fairly constant speed, and it produces a shock wave along the way, let's go ahead and put an observer here, which is close to the gun in terms of the x-axis, if you want to say it, but the downrange distance is small, and the cross range distance is large. And then over here we're going to put an observer whose downrange distance is large, but the cross range distance is small. So in this case, this example is what is done in figure 1, and this one is done in figure 2. And so using their colors, the muzzle wave, of course, is a direct path from the tip of the gun to the observer. So in figure 2 it's that, and in figure 1 similarly it's like that. Now the shock wave, in the case of 1, is going to be produced very close to where the observer is, and so it's that little thing there. Whereas over on case 2, the shock wave is going to be produced very close to the tip of the gun and travel almost an identical path as the muzzle wave. So in case 2, now this is for one shot, 2 observers, same bullet, we're going to have different times of arrival. And in case 2, the arrival time is going to be approximately 0. 0 meaning less than 100 milliseconds. Whereas over here, the arrival time for the muzzle wave is much larger, and the shock wave is small, because the time of arrival is the sum of the just time that it takes the bullet to reach this point, and then the sum of the time at the speed of sound it takes for the sound wave to travel along that little red line. So over here, depending upon how far away, it's going to be much, much larger than 0. So that's what I'm trying to say. And if you had other observers at other locations, if we had, for example, an observer up here where the cross range distance is about the same size as the downrange distance, then again you're going to have a whole different story completely. The muzzle wave comes up to reaches the observer, and then we were using red. The shock wave would probably be generated somewhere in here and reach that observer, and it's got a fairly long path compared to case 1, but shorter than case 2. So in this case, the time difference of arrival between these two is going to be somewhere between 0 and less than much, much greater than 0. And it really would depend upon, the downrange distance. So one bullet, multiple different lags, where lag is defined as the time of arrival difference between the shock wave and the muzzle blast, the shock wave arriving first. Alright. And I just want to make that clear. Now we're going to go back over to their diagrams. And because this paper has also some other clear and interesting things in it. So on their diagram, you can see how they had the conic shock wave here with the little red angle, I guess you would call it, right there near the bullet, and how that shock wave propagates parallel to the cone out to the observer along a path and reaches it, and then how the muzzle blast propagates from the tip of the gun along a direct path to the microphone, and how for this case where the angle of fire is large, and they don't really define large here because it's a function of many things, then these two arrive closer and closer together the larger that angle. In fact, there is an upper limit based upon the speed of the bullet at which they arrive identically. And this will be the case, for example, when you have in Vegas you have Oasis Apartments, because the angle between the bullet path and where the Oasis is large, or somewhat so for the Excalibur, because again where the bullet is going is towards the venue, but the Luxor would be way over here, so that angle is large. But when you take places like the cops down on the corner where they're almost directly beneath the line of fire, then you have to go back up to this case, and the shock wave propagation time between where it leaves the line of fire and the microphones is small, and therefore the time of arrival between the muzzle blast and the shock wave is much larger. Now, don't get me wrong, the time of arrival here for the shock wave is the sum of the time that it takes to travel to the point where the shock wave leaves the path and then goes to the microphone. So it's not exactly 0. But this region up here is traveling at the speed of the bullet, and so it gets covered very quickly even though it's a long path. So it's that distance, which we call d, divided by the speed of the bullet, plus this little red thing here, which is, we'll call it a divided by the speed of sound. But in the case where you're close, these two are still going to be much, much shorter, and hence the shock wave arrives sooner than this slow lumbering muzzle blast wave traveling at the speed of sound over a slightly smaller distance. Alright. But I like their graphs, and I think, or their pictures here, and I think ultimately I'm going to adopt something similar to this. Alright, so let's go on and read some more through their paper. And here they're talking about the shock wave, how it's produced by the bullet in a manner similar to the triangular wave of a wake of a boat created on a surface of the water, and that the tip of the cone moves along the line of fire at the speed of the bullet, not the speed of sound, but the speed of the bullet. But the acoustic wave that leaves it, these red dotted lines, travels at the speed of sound, perpendicular to, i.e. at a 90 degrees, to the shock wave itself, or parallel to the conic front. Okay. And then they go on to cover what we just covered about how to calculate the shock time, where it's the sum of the distance of the bullet traveled plus the sum of the shock wave propagation distance over the speed of sound. And then they go on to say that for a high angle of fire, namely that angle is large, the point of detachment of the shock wave is close to the weapon. That is, the larger the angle, the shock wave that you hear or get recorded is close to being close to the gun. And in fact, when you hear it, this is one of the times where you could listen to both the muzzle blast and the shock wave, the crack, and they both to your ears and to your mind be coming from very similar positions. Whereas up here in the first figure, when you hear the snap by itself, you're going to turn to the source of the sound, which is over along the line of fire, which is almost at 60 to 80 degrees away from the direction where the weapon was fired from. So when the lag is large, the shock wave does not point to the source of fire, it points to the source of the sound, which is the bullet, which is close and almost at a 90-degree angle to the muzzle blast wave. Alright, so back down to the reading here. And then they go on to say how these for large angles are the same and short angles are bigger. Now they go into a little bit about what those signals would look like if they were recorded or converted to an electrical impulse. And they start out by giving an idealized waveform. And they don't give any time scale or any to this, but the first part is the shock wave, and this is what we call the classical N wave because it looks like the letter N. It goes up, representing the high overpressure that the tip of the shock wave, tip of the bullet produced into the shock wave, and then it goes down in a ramp function, i.e. a linear motion, to a low underpressure because everything has to go back to normal pressure, and then it does by coming back up fairly quickly to the normal pressure. And the shock wave arrives first, and then sometime later you get the muzzle blast. Now this is an ideal muzzle blast, which it goes up to a high overpressure, comes down very, very quickly with a little overshoot, and then gradually goes over to the normal pressure. And then they show a couple of more realistic images. Now, and this is starting to get close to what I've been talking about now for a couple, 3 months, where, let's get some, we have this first line, which is the shock wave, which is produced by the bullet, and then we see a ground reflection, probably right there at that little bitty spot, almost looks like a double take, and then we see another reflection. These are all probably from the ground, and then some, and these are all very big and prominent and easy to observe. But then sometime later, way out here, we get the muzzle blast, which almost looks non-existent. And that's an amplitude versus time, and the scale is 0.2 seconds. So in this case, the distance between the shock wave, the primary shock wave, and this is probably on the order of 0. Certainly greater than a tenth, but let's call it 150 milliseconds, or 0.150 seconds. Which, if it were a 223 round and being fired at Vegas from an elevated position, you could just go directly to my lag map and look at all the regions where that lag would hold to be true. So in this case, this isn't a large angle between the fire of the gun and the observer, but it's also not an extremely small one, although it could be a small angle that's not too far away from the shooter. Then they do a power graph here, which is much like the spectrograms that I use, which are the power dBs, and this is a measure of energy. Now, kind of interestingly enough here, let's go to green now. They point out several things. First off, this background noise, which is really, really small. And then you see the primary shock wave come up big, and then, as in many cases in Vegas, you see this exponential decay over time. And that's indicative of a lot of reflections. And here they call it reverberation. And then the text, they go out to point that this was a field test where it was on a surface down a corridor that was large, that was flanked on both sides by trees, and that this reverberation, or these multiple echoes, were caused by both the ground and the trees. The sound hits the trees, reflects back onto the ground. The bullet sounds hit the ground, reflect onto the trees, and they come back to their microphones. And then they point out how, in this case, you still get secondary shock wave reflections. A couple, actually 4 of them total. Where's the first one? Over here somewhere. They just don't show it much. And then you see the muzzle blast and a muzzle blast reflection, probably from the ground or something nearby. So that's a very realistic signal. And I guess I could have observed, well, anyway. And then this again is at the 0.2 second range. So, it's not a large lag, but it's not a small lag either. But it's certainly separated enough between the shock wave and the muzzle wave that you could hear it. And then they amplify this region to the left, and then they amplify the region to the right to show you on an amplitude scale what this looks like in more detail. So here we see the classical N wave for the shock wave, and you'll notice that since the time is 10 milliseconds for the entire picture there, this has to be much, much quicker than a millisecond. So that means that they're sampling at a pretty high frequency. They're probably sampling at close to 100 kilohertz, because with 44 kilohertz, which is what it's in Vegas, you can't even get near that representation. So then you see a primary shock wave, and then you see some distorted reflections, because that's what reflections are. They're distorted and scaled down versions of the original wave. Then you see another reflection. Who knows what it came from, but it's got more energy in it, larger amplitudes than the first reflection. And you'd have to know a little bit about the environment, but you could calculate the distance from the time between these. For example, this reflection being let's see, the whole scale is 10 milliseconds. That's probably on the order of 0.0008 seconds, or 0.8 milliseconds, and I would guess that this one is the ground wave. And then this distance covers probably 6 milliseconds. Let's say 6 milliseconds, or 0.006 seconds. And so if the speed of sound were, say, 1100 or 1200 feet per second, then that's approximately let's say 9 feet, or let's call it 10 feet for easy calculation. And since reflections come with both, it's divided, it's twice the length at which the path of travel is. So then this one is really, really close. That's got to be a ground reflection, or something very, very close to the gun at which it was reflected. And over here at 10 feet, that one could either be the ground or something, but they're both close by. Alright, and then lastly, they go down here to a magnification of what we had up there, right in these yellow circles, of the muzzle wave to show you what it looks like. And again, this is even on a larger scale than the shock wave. This is on, let's erase some of this crud first, because it's getting kind of confusing. Okay. So here we have the muzzle blast on a 20 millisecond scale. So it's, well, I don't think we really want that large a dot. There we go. So this time from there to there, which is about one cycle, I would say is 1/5 of that. So that's probably about 4 milliseconds, which is not too atypical of a muzzle wave. A little larger than a 223 round, so that's probably a little bit larger caliber than a 223 round. Probably a 30 caliber or something like that. Anyway, so those are real examples that this company is providing that bears strong resemblance to what I've been explaining over the months. And I thought that these pictures and diagrams were, clear enough to maybe enhance what I've been telling you. So let's see what else they have to say, if anything. I'm reading through it to see if I missed anything. And they say how the background sounds can actually... No, and then they're going to go into, probabilities of detection and detection and what other systems should be. But I primarily wanted to show you these two examples of a small angle of fire and a large angle of fire to emphasize what I've been saying. So anyway, that's pretty much it, and we'll grab you in the next one.